Yes, even when a generator is isolated from the grounding system, there is the potential for touch voltage on non-current carrying metal parts of the generator, such as the frame or enclosure. This can occur if there is a fault in the generator's electrical system that causes current to flow through the metal parts. The potential for touch voltage is typically addressed by bonding the non-current carrying metal parts of the generator to the frame and grounding the frame via a grounding electrode. A more complete answer requires manufacturer's instructions and field conditions. The specific requirements for grounding a generator are outlined in the National Electrical Code and may vary depending on the size and type of generator. For more specific information, consult the latest version of the NEC. Touch voltage, in the context of electrical systems, refers to the potential voltage a person could be exposed to if they were to simultaneously touch two conductive surfaces. This voltage arises due to a fault condition within the system, causing current to flow through unintended paths, such as the metallic enclosure of equipment. When a generator is isolated from the grounding system, meaning it's not directly connected to earth ground, this doesn't inherently eliminate the risk of touch voltage. The reason is that a fault within the generator can still energize the metallic parts. For example, if a wire's insulation were to fail inside the generator, creating a short circuit between a live conductor and the generator's frame, the frame would then be at a voltage potential relative to earth. If a person were to touch the energized frame while simultaneously touching something grounded, it would experience touch voltage, resulting in an electric shock. Bonding the non-current carrying metal parts to the generator frame is a crucial safety measure. Bonding creates a low impedance path for fault current to flow back to the source, which is the generator windings in this case. This low impedance path facilitates the rapid operation of overcurrent protection devices, such as circuit breakers or fuses, which will then quickly interrupt the circuit and de-energize the faulty equipment. Without effective bonding, the fault current may not be high enough to trip the overcurrent protection device, leaving the metallic parts energized and posing a continuous shock hazard. Grounding the frame through a grounding electrode provides an additional layer of protection. The grounding electrode establishes a connection to the earth, which serves as a reference point for voltage. In the event of a ground fault, the grounding electrode helps to limit the voltage rise in the generator's frame, reducing the potential for touch voltage. Moreover, it provides a path for fault current to flow back to the source through the earth, aiding in the operation of overcurrent protection devices. The National Electrical Code, or NEC, provides detailed guidelines and requirements for grounding and bonding electrical systems, including generators. These requirements are designed to minimize the risk of electrical shock and fire hazards. Section 250 of the NEC covers grounding and bonding in detail, addressing various aspects such as grounding electrode systems, equipment grounding conductors, and bonding methods. The specific NEC requirements for generators can vary based on several factors, including the size of the generator, whether it's a portable or stationary unit, and its application. For instance, a small portable generator used for temporary power might have different grounding requirements than a large stationary generator used for emergency backup power in a commercial building. Some generators may be required to be connected to a grounding electrode system, while others may be permitted to be isolated from ground under certain conditions. The NEC also specifies the types of grounding conductors and bonding jumpers that must be used, as well as the methods for connecting them. It's essential to consult the latest version of the NEC and any applicable local codes to ensure that generator installations comply with all relevant requirements. Furthermore, it's always recommended to follow the manufacturer's instructions for the specific generator being installed. Manufacturers often provide detailed information on grounding and bonding requirements, as well as other safety precautions. Ignoring these instructions can lead to unsafe conditions and may void the generator's warranty. In addition to grounding and bonding, other safety measures can help to minimize the risk of touch voltage and other electrical hazards associated with generators. These measures include using ground fault circuit interrupters, or GFCIs, on circuits supplied by the generator, regularly inspecting the generator and its wiring for damage, and ensuring that the generator is properly maintained. It's also important to educate users about the potential hazards of generators and how to operate them safely. This includes warning them not to touch the generator or any connected equipment while it's running, and to avoid using generators in wet or damp locations. By following these safety precautions, it's possible to significantly reduce the risk of electrical accidents involving generators. Understanding the principles of grounding and bonding is crucial for ensuring electrical safety. Grounding and bonding are not the same thing, although they are often used together. Grounding refers to connecting an electrical system or equipment to the earth, while bonding refers to connecting together all of the non-current carrying metal parts of an electrical system. The purpose of grounding is to provide a low impedance path for fault current to flow back to the source, which helps to protect against electric shock and fire hazards. The purpose of bonding is to create an electrically continuous path for fault current, which also helps to protect against electric shock and fire hazards. In a properly grounded and bonded electrical system, if a fault occurs, the fault current will flow back to the source through the grounding and bonding conductors, causing the overcurrent protection device to trip and de-energize the circuit. This prevents the metallic parts of the equipment from becoming energized and posing a shock hazard. There are several different types of grounding systems that can be used, depending on the application. These include grounded systems and impedance grounded systems. Grounded systems are the most common type of grounding system, and they are used in most residential and commercial buildings. In a grounded system, one of the conductors, typically the neutral conductor, is intentionally connected to ground. And grounded systems are sometimes used in industrial applications where it is important to maintain continuous operation, even in the event of a ground fault. In an ungrounded system, none of the conductors are intentionally connected to ground. Impedance grounded systems are used in some industrial applications to limit the amount of ground fault current that can flow. In an impedance grounded system, a resistor or reactor is connected between the neutral conductor and ground. The NEC provides detailed requirements for each type of grounding system. The NEC also provides requirements for bonding. Bonding is required for all non-current carrying metal parts of an electrical system, including metal conduits, metal enclosures, and metal equipment frames. Bonding conductors must be sized according to the NEC, and they must be properly connected to ensure a low impedance path for fault current. In addition to the NEC, other standards and regulations may apply to grounding and bonding, depending on the location and application. These may include local building codes, industry standards, and Occupational Safety and Health Administration, or OSHA, regulations. It is important to consult all applicable standards and regulations to ensure that electrical systems are properly grounded and bonded. Proper grounding and bonding are essential for electrical safety. By following the NEC and other applicable standards and regulations, it is possible to minimize the risk of electric shock and fire hazards. It is important to note that electrical work should only be performed by qualified and licensed electricians. Working with electricity can be dangerous, and it is important to take all necessary precautions to protect against electric shock. Always de-energize circuits before working on them, and use appropriate personal protective equipment, or PPE, such as insulated gloves and safety glasses. If you are not qualified to perform electrical work, it is best to hire a licensed electrician. In summary, touch voltage is a potential hazard associated with generators, even when they are isolated from the grounding system. Bonding the non-current carrying metal parts of the generator to the frame and grounding the frame through a grounding electrode are crucial safety measures. The NEC provides detailed requirements for grounding and bonding generators, and it is essential to consult the latest version of the NEC and any applicable local codes to ensure compliance. Additionally, following the manufacturer's instructions for the specific generator being installed is crucial. Other safety measures, such as using GFCIs and regularly inspecting the generator, can further minimize the risk of electrical hazards. Understanding the principles of grounding and bonding is essential for ensuring electrical safety, and electrical work should only be performed by qualified and licensed electricians. The concept of impedance plays a significant role in understanding fault current flow and the effectiveness of grounding and bonding. Impedance is the total opposition to current flow in an alternating current, or AC, circuit, and it includes both resistance and reactance. Resistance is the opposition to current flow due to the material's properties, while reactance is the opposition to current flow due to capacitance and inductance. In a fault condition, the impedance of the grounding and bonding path determines the magnitude of the fault current. A low impedance path allows for a high fault current, which will quickly trip the overcurrent protection device. A high impedance path, on the other hand, will limit the fault current, which may not be sufficient to trip the overcurrent protection device, leaving the metallic parts energized. The NEC specifies the minimum size of grounding and bonding conductors to ensure that they have a low enough impedance to safely carry fault current. The size of the conductor depends on the size of the circuit and the available fault current. It is important to use the correct size conductor to ensure that the grounding and bonding system is effective. Another important factor in grounding and bonding is the quality of the connections. Loose or corroded connections can increase the impedance of the grounding and bonding path, which can reduce its effectiveness. All grounding and bonding connections should be clean, tight, and free of corrosion. The NEC specifies the methods for making grounding and bonding connections, and it is important to follow these methods to ensure that the connections are reliable. The grounding electrode system is another important component of the grounding system. The grounding electrode system provides a connection to the earth, which serves as a reference point for voltage. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or underground metal water pipes. The NEC specifies the requirements for grounding electrodes, including the type of electrode, the size of the electrode, and the depth at which it must be installed. The grounding electrode system must have a low enough resistance to ground to effectively limit the voltage rise in the electrical system in the event of a ground fault. The resistance to ground of the grounding electrode system can be measured using a ground resistance tester. If the resistance to ground is too high, additional grounding electrodes may be required. Ground fault circuit interrupters, or GFCIs, are an important safety device that can help to protect against electric shock. GFCIs work by monitoring the current flowing in the circuit. If the current flowing out of the circuit is not equal to the current flowing back into the circuit, the GFCI will trip and energize the circuit. This indicates that some of the current is leaking to ground, which could be due to a fault condition or a person touching a live wire. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of electric shock. They are also recommended for use with portable generators and other equipment that may be used in wet or damp locations. Arc fault circuit interrupters, or SIs, are another type of safety device that can help to protect against electrical fires. SIs work by detecting arc faults, which are small electrical sparks that can occur when there is a loose or damaged wire. Arc faults can generate a lot of heat, which can ignite nearby combustible materials and cause a fire. SIs are required in many locations, such as bedrooms, where there is a high risk of electrical fires. Regular inspection and maintenance of electrical systems is essential for ensuring electrical safety. Electrical systems should be inspected regularly by a qualified electrician to identify any potential problems, such as loose wires, damaged insulation, or corroded connections. Any problems that are identified should be repaired promptly to prevent them from becoming a safety hazard. The electrical equipment should also be maintained according to the manufacturer's instructions. This may include lubricating moving parts, cleaning contacts, and replacing worn or damaged components. Proper maintenance can help to extend the life of electrical equipment and prevent it from causing a safety hazard. Education and awareness are also important for electrical safety. People should be educated about the potential hazards of electricity and how to avoid them. This includes warning them not to touch live wires, to use caution when working with electricity, and to call a qualified electrician if they have any concerns about their electrical system. Electrical safety awareness programs can help to promote safe practices and prevent electrical accidents. In addition to the technical aspects of grounding and bonding, there are also some practical considerations that should be taken into account. For example, when installing a generator, it is important to choose a location that is dry, well ventilated, and away from combustible materials. The generator should also be properly supported and secured to prevent it from tipping over. When connecting the generator to the electrical system, it is important to use the correct size and type of wiring and to follow all applicable codes and regulations. It is also important to label the generator and the circuits that it supplies so that they can be easily identified. When operating the generator, it is important to follow the manufacturer's instructions and to avoid overloading the generator. Overloading the generator can damage the generator and can also create a safety hazard. It is also important to monitor the generator for any signs of problems, such as unusual noises, smoke, or sparks. If any problems are detected, the generator should be shut down immediately and inspected by a qualified technician. By following these practical considerations, it is possible to safely and effectively use a generator to provide power when needed. The NEC is a comprehensive document that covers a wide range of electrical safety topics. It is important for electricians, engineers, and other electrical professionals to be familiar with the NEC and to follow its requirements when designing, installing, and maintaining electrical systems. The NEC is updated every 3 years to reflect the latest advances in electrical technology and to address new safety concerns. It is important to use the latest version of the NEC to ensure that electrical systems are safe and compliant. The NEC is available from the National Fire Protection Association, or NFPA, and can be accessed online or purchased in print form. In addition to the NEC, there are also a number of other standards and regulations that may apply to electrical systems depending on the location and application. These may include local building codes, industry standards, and OSHA regulations. It is important to consult all applicable standards and regulations to ensure that electrical systems are safe and compliant. Electrical safety is a shared responsibility. Electricians, engineers, and other electrical professionals have a responsibility to design, install, and maintain electrical systems that are safe and compliant. Building owners and managers have a responsibility to ensure that their electrical systems are inspected and maintained regularly. And individuals have a responsibility to be aware of the potential hazards of electricity and to take precautions to avoid them. By working together, we can create a safer electrical environment for everyone. In conclusion, understanding touch voltage, grounding, bonding, and the NEC requirements is crucial for ensuring electrical safety, especially when dealing with generators. This knowledge, combined with practical considerations and adherence to safety standards, helps to minimize the risk of electrical hazards and protect individuals from potential harm. Always consult with qualified professionals for electrical work and stay informed about the latest safety guidelines and regulations.